Hi there. In this section, we're gonna, I'm a little short. In this section, we're gonna start indefinite integrals. It's a nice short section. So let's get started. Not a lot of theoretical stuff going on here. So what I wanna go over, there's only 3 examples. They're all like 2-part examples, but still relatively short. The idea is that we're gonna be using what we learned in the previous section, where the first part of the fundamental theorem of calculus says that this expression here is an antiderivative of f. Just means if you take the derivative of this, you get f of x. And then we used that to prove part 2, which says that to evaluate a definite integral, we need to find the antiderivative or some antiderivative, and then plug in b and a. So that's what we're going to be doing today. Not real fancy. So the symbol that we show you today is this antiderivative symbol. And it's called an integral, but if you want to call it an antiderivative, it's exactly the same thing, right? And it just gives you some antiderivative of f. And it's called an indefinite integral. So integral refers to the integral sign. And for those of you who have the textbook, oops. I think now you understand why they put this on the cover of the textbook. So this just means that we're finding an antiderivative, right? So let's jump right in. Oh, sorry, one more thing before we jump in on the examples. Don't forget we have 2 different things now that both have this symbol, right? One is the definite integral, where there's 2 numbers here, or a number in a function. Well, this gives you a number. This is not a function of x. If it's a function of one of these 2 things. And if these are both numbers, it's a number. But an indefinite integral is a function, right? So it's more like what we saw earlier with derivatives, right? It's just a function of x. So it tells you at any point x what the antiderivative is of that function. And again, here's the connection. So we're going to be using this notation here. So the definite integral from a to b of f of x dx is the indefinite integral of f of x evaluated at b and a, which means the same thing as antiderivative with b plugged in minus antiderivative with a plugged in. So we're going to do all this stuff. This is basically what we're doing today. Here's a table. This is just common rules and stuff. We went over this when we went over antiderivatives. But again, just notice a couple of things. I'm going to be not showing all of the details just because we've seen this already with antiderivatives. And it's actually the same rules as derivatives, right? So like constants. If I have an integral out front of a constant times a function, I can just push the integral all the way in and pull the constant out, right? So that's a common thing. Just get used to it. We're going to do it a lot. And then here's another one, right? If I have addition, I can take the integral and split it into 2 pieces and evaluate 2 separate integrals. However, that's not how I'm going to write it out, because what ends up happening is that if we have the sum of 2 functions, that's still just one function, right? So the idea is you could split that integral, evaluate the integrals, and then separate it back out. There's really no point in doing all that work. I'll show you kind of the amount of work I expect you guys to show. It's about the amount of work that most people show. Very few people show every detail, because by the time you get to this point in the class, we've accumulated a lot of rules, and the stuff should start to look familiar, even if we do have some new symbols that you haven't seen before. All right. Oh, and if you want a larger list of integrals, there's a list in the back of the book. Your calculus cheat sheets would have them. Just Google it, you know. Lists of integrals are not hard to come by. Let's put it that way. All right, so let's jump in and do example 1 here. So let's just, before we jump in, let's look at what we have here. So this is just the definite or indefinite integral, or again, you can call it antiderivative fourth root of x cubed dx. And then here we have the same antiderivative, except there are limits. It goes from 1 to 16. So let's see what's the same and what's different when we do a problem like this. So here we look at this and we say, I don't know how to evaluate this. You need to have x to a power. So you can use the rule in the table. And the rule says the antiderivative of this, you add 1 to the power and divide by the new power. Right? We actually proved that this was true back in 3.9. And of course, you tack on a plus c. You're allowed to leave it like this, but you may want to simplify it a little bit, just in case you need to look for cancellation, because sometimes terms cancel and stuff. Simplify it a little bit. Don't go too crazy. Especially constants, right? Maybe you can pull some constants out front or cancel them. So this is a real nice answer. And again, just like in 3.9, you can check your answer by taking the derivative. So the derivative of this, right, multiply the power. So 7/4 times 4/7 is 1. Drop the power by 1. 7/4 minus 1 is 3/4. And then the derivative of a constant is 0, and you just get x to the 3/4. So you don't have to show a ton of work for this stuff, okay? Now, what about the second part of the problem where we put limits on the integral? What changes? So this is a definite integral, and so we need that capital F of b minus capital F of a. So we write it in the form where here's our antiderivative. Remember, it's any antiderivative. You don't have to write the plus c. Right, so this is just that without the plus c. And then I'm going to evaluate this. Now you can evaluate it just like this. I just want to show you something that I like to do. If I can factor out constants, I always factor them out. So that's what I did here. And it gave us like a slightly new notation, because now that 4/7 is in the front, so when I evaluate it, I'm not goofing around with a bunch of weird fractions. I'm going to multiply that fraction through at the end. Well, I know what 16 to the 7/4 is, right? That's 2 to the 7th. I know how to do 128 minus 1, and I can multiply that by 4 and get 508. So this might look like a lot of work, because some of you are thinking, well, can't I just type this into my calculator, or couldn't I evaluate this and type it into my calculator? Sure, but your calculator might give you a decimal answer. The homework will not accept decimal answers for this, and on a test, I don't want decimal answers. So this is anything you can do to simplify the arithmetic. I suggest that you do it. Now, if there's nothing you can do to simplify the arithmetic, then there's nothing you can do. But in this case, there is, right? Factoring out that constant really helped make it a much easier problem. And you can see clearly indefinite integral gives us a function or a family of functions. Definite integral gives us a number. These are not the same thing at all. Even though it starts off looking similar, they mean different things. Just a convenient way to reuse the notation. All right, let's jump in and do another one. So we're going to do, well, before we move on, let's look at them again. So is there any way I can rewrite this? Because you might look back at your table of integrals and go, I don't see, something plus something divided by something on my integral list because it's not there. Same thing here, right? We have a negative something plus something divided by something. What do? Well, remember, when you're doing derivatives, think back to chapter 2. When you were doing derivatives, you always wanted to distribute everything or FOIL everything. Well, this is the same idea here. We want to put this in a form that we know how to work with. So for the first one, 6 over cosine squared theta is just 6 secant theta. And 4 cosine squared theta over cosine squared theta is just 4. Now, I am allowed to take this integral and break it up into 2 separate integrals. But, because you might think, oh, well, this is a function and this is a function. But remember, we're just going to break it up and then separate it again. So we might as well just keep it separated. So I can, just using the rules of antiderivatives, which are the same rules as derivatives, for constants and distributing, I can ignore this 6 and just do the integral from 0 to pi over 4 of secant squared theta. Plus, and again, I can ignore this 4, and I can do another integral of d theta. Right? So what do I get? Well, 6 stays the same. Integral of secant squared theta is tangent theta. Integral of 4 is 4 theta. We have a rule for that from antiderivatives. And then I just evaluate from 0 to pi over 4. So here's that alternative notation where I put it in brackets. So this means take this entire expression, plug in pi over 4, subtract this entire expression with 0 plugged in. And we know what all this is, right? Tangent of pi over 4 is 1. 4 times pi over 4 is pi. Tangent of 0 is 0, and that's 0. So you just get 6 plus pi. Nothing too fancy going on here. So when it comes to how much work you should or shouldn't show, it's completely up to you. Some of the solution guides, answer keys, and book examples will show this broken up. But I'm just trying to convince you that because we know that we have a rule for constants and a rule for sums and differences, that you can just evaluate these separately. You don't have to show that. It's going to save you a lot of time. There's going to be problems that take a long time to do, starting in the next section. The next section has some really long problems in it. All right, well, let's do the next one. So this is an indefinite integral, so we should get a function for our answer. And just like before, simplify first, right? So here we have negative 2t cubed over t, well, that's just negative 2t squared, plus radical t over t, it's just t to the minus 1/2. Now, this is an indefinite integral. I'm allowed to split it, and I'm allowed to just push the integral up next to the functions, but we know we can do that. We did this when we did antiderivatives. So it's just going to be negative 2 times the integral of this, which is t cubed divided by 1/3. I'm sorry, divided by 3, right? So it's just negative 2/3 t cubed. And then here, we increase the power by 1, divide by the new power. You might want to simplify a little bit, maybe change the fraction exponents back to radicals. And that's your answer. Again, I'm not going to get real bent out of shape if you're not showing tons of work. It just has to make sense. Like, it's the same rules that when we did limits, we did derivatives, and I said you don't have to show the constant rule, you don't have to show the sum and difference rule. Those are the only rules I'm not showing, because it's going to save you 2 or 3 minutes per problem, and that's a decent amount of time. All right, let's keep moving. Oh yeah, and it's an indefinite integral. Don't forget the plus c, right? Also, don't forget to check your answer. So the derivative here, multiply the 3, we get negative 2, drop the power by 1, so we get 2, so negative 2t squared. And then here, this is t to the 1/2. 1/2 times 2 is 1, so the 1 goes away. And then drop the power by 1, 1/2 minus 1 is negative 1/2. There you go. All right, next up, I'll let you guys read that. I just want to get into the example here. This is very similar to what we did in 3.9. So the displacement is just where the particle ends up relative to where it started. The total distance is just if the particle is moving backwards, we take the absolute value. So let me go back and show you the formulas. Here's the formulas we're going to use. So the integral of the velocity from t1 to t2, it just gives us a change in position. So we take the position function, type in t1, minus the position function with t2. So this is just the net change. So how far does the particle end up from where it started? It does not take into account if it moved forward a whole bunch and moved backwards a whole bunch. It's just the two endpoints. How far is it from where it started? However, something different goes on when we want to do total distance traveled. And we did one like this earlier in the class. And you had some on your homework, and there was one on the, I don't know if I put one of these on the test or not. I can't remember. And the idea is that we have to take the integral of the absolute value of the velocity, which is the speed. So we're going to use the same concept, except now that we have integral signs, the symbols, it actually gives us a more compact way to write this stuff, as you will see. All right, so here's our formula for displacement. We have an integral of v of t, so we just want to take the integral. V of t is t squared minus 2t minus 8. We don't care where it's positive and where it's negative, so we just take the integral. And again, notice I'm not like distributing that integral, right? You're allowed to just take the integral of each part and just keep the plus signs where they are, keep the minus signs where they are, and keep the constants where they are. So here, the integral is, t cubed divided by 3, so it's 1/3 t cubed. This is t squared divided by 2. And this is just 8t. And all the minus signs stay the same. Evaluate this from 1 to 6. So we just plug 6 in the whole thing, and then subtract and plug 1 in the whole thing. Don't forget to distribute this negative. So there's no real easy way to simplify this. So I just typed it in a calculator, got negative 10/3. Again, must be a fraction, if possible. And that's your answer. So the integral of the velocity is the position. So this particle started off negative 10/3 meters behind where it started. Let's do the second part. Let's look at total distance traveled. So here it's the absolute value of v of t. So we need to determine if this particle is ever moving backwards. If the particle only moves forward, then we can ignore the absolute value. But it's pretty obvious it moved backwards because the answer to the first part was negative. So we know it moved backward at least part of the way. So let's find out where it's 0, and then we can just plug in numbers and see where it's positive and where it's negative. So I need to find out something about this function. I need to find out where it's positive and where it's negative. So first I find out where it's 0. Luckily this factor is real nice. Negative 2 is not in our domain, so I can ignore it. So the velocity is 0 when t equals 4. I don't know when it's positive and when it's negative. I got to plug some numbers in, right? So I just do some side work. I plug in 2. Plug 2 in here, right? You get negative 2 times 4, you get negative 8. That's negative. Plug in 6. You get 2 times 8. You get 24, which is positive. Big deal, right? This just tells us negative and positive, which is all we need. Now, I rewrite this with this absolute value. I know it's negative on the interval 1 to 4. I know it's positive on the interval 4 to 6. So look at what I did here. I split it into two integrals, 1 to 4 and 4 to 6. The positive one I don't mess with at all. Where the particle's moving forward, but where the particle's moving backwards, I need this answer is going to be negative. Right? And I need the positive value of that. So I'm just going to put a negative out front. Whatever this number is, it's going to be negative. So it's going to be a negative number, but the negative will make it positive. This is a lot easier than the ways we did it earlier in the class. Being able to just pull a negative sign out. Now watch what we do next. This is very, very easy. You guys should practice this technique. It will definitely be on an exam. Anytime I have a negative of an integral, I can just switch the bounds and make it positive. That's what I do on the next slide. So I made this positive and just made this from 1 to 4. Now I'm evaluating my original function. I already know what the antiderivative is, and I just have to plug in all the bounds, right? The antiderivative is this. I already found it. So I'm doing this antiderivative from 4 to 1 plus this antiderivative from 4 to 6. I know that sounds weird, but this is how you do this because I'm not fiddling around with a bunch of negatives. I can just plug everything in, type it into a calculator, and I get 98 thirds meters. That's the way to do a problem like this. Stay organized, keep track of everything, and just use the properties we have. So if you need to put a negative out here, just switch those and take the negative away. So it's a nice property, and it makes doing problems like this fairly easy. All right, well, that's it for today. If you guys have any questions, let me know. Post on the discussion forum or email me. And I'll see you guys next video. All right, bye-bye now.